you remember this guy, Pascal. Bonjour! He came up with this pattern of numbers that we refer to as Pascal's triangle. And in this lesson, we're going to see how we can relate Pascal's triangle to the binomial theorem. You may have previously used Pascal's triangle to expand binomials that are to some exponent n. But in this lesson, we're going to see how we can relate that with combinations. And if the exponent on the binomial is large, can we solve or expand it without needing to draw Pascal's triangle all the way to the appropriate row? Well, let's take a look and see what we can find. First, let's see how Pascal's triangle relates to combinations. The right-hand triangle in red is Pascal's triangle written out, the first 5 rows. Remember that we refer to the very top row as row 0, and then every row below it goes row 1, row 2, and so on from there. And then also remember that the first number in each row we refer to as position 0, and then position 1 and position 2, and so on. The left-hand triangle in purple gives us the notation for all of those positions. We refer to them as, term 3-1 or term 4-3. Well, how do combinations relate to both of these? Well, there's an interesting thing that we can see. Take a look at this. In between these two triangles, I've now included a third triangle. Notice how this triangle has the same number of rows and the same number of terms as the other two triangles. In fact, each one is a different combination. The first one at the top being 0, choose 0, and then the next row down is 1, choose 0, and 1, choose 1, and then 2, choose 0, 2, choose 1, and 2, choose 2, and so on and so forth. Well, you may notice that this relates to the position numbers that each number is in Pascal's triangle. For instance, position 3, 2 in Pascal's triangle is in the same spot as the combination 3, choose 2. And position 4, 1 is in the same spot as the combination 4, choose 1. Well, it also turns out that the combinations that are in those positions equal the appropriate number in Pascal's triangle. So 3, choose 2 happens to equal 3. And 4, choose 1 happens to equal 4. And this pattern will continue for every single row of Pascal's triangle, which makes it really easy for us to solve any given row of Pascal's triangle just by knowing what row number we're looking for. I may not need to have to draw out the 6th row and the 7th row and the 8th row and so on if I want to get all the way down to row 10 or row 20 or row 50. I just need to know that each number in Pascal's triangle can be derived by knowing what row number it's in and also what position number it is, because it will equal the combination of those two things. Okay, this will be helpful later on. But let's try expanding some binomials and we'll see how these combinations can help us. First, let's start with expanding a plus b all to the exponent 2. The normal way we would expand this is to just write it out. A plus b to the exponent 2 is the same as saying a plus b times a plus b. You've probably been taught that when you have a binomial times a binomial, an easy way to do this is to use FOIL. So we could multiply the first term times the first term times the last term, the second term times that middle term there, and then that term times that one. First, outside, inside, last. So when we do this, we get this as our expansion. And then we can simplify this by just combining those like terms, the AB terms. So we end up with a squared plus 2ab plus b squared. Simple enough. So what happens when we want to go a bit bigger? Let's now try to expand a plus b cubed. So, just like before, let's make our first step to write this out. A plus b times a plus b times a plus b. We can sort of see here that the first two a plus b terms, well, that's just like the question we had before where it was a plus b all squared. So I can replace that a plus b times a plus b with the answer that we had from above. Now we have a trinomial times a binomial. So just like we did with FOIL before, we're going to do the same thing and expand one of these into the other brackets. It's not quite FOIL, but it's the same sort of method. We're going to take the a squared and multiply it by the a, and then we're going to take the a squared and multiply it by the b. And then we're going to take the 2ab and multiply it by the a, and the 2ab and multiply it by the b, and then finally the b squared multiplied by the a, and the b squared multiplied by the b. So it's sort of like a FOIL, but because it's a trinomial and a binomial, we can't really use the letters in FOIL. We end up with this as our expansion. There's 6 total terms there. Some of them are like terms. You can see the a squared b's are like terms, and the ab squareds are all like terms. So if we collect those, we end up with this. A cubed plus 3a squared b plus 3ab squared plus b cubed. The one thing I want you to notice is the different coefficients that are in front of each of these 4 terms. The a cubed and the b cubed both don't have a coefficient, or there actually is a coefficient, it's just the number 1. And the 2 middle terms have the coefficient of 3. Where have we seen those 4 numbers before? So what happens now if we want to increase the exponent on the binomial further? We've seen squared and we've seen cubed. What happens when we now want to look at a plus b to the exponent 4? Well, here's what the expansion would look like. A to the exponent 4 plus 4a cubed b plus 6a squared b squared plus 4ab cubed plus b to the exponent 4. Again, the thing I really want you to look at here is the coefficients in front of each term. We have 5 different terms, and the coefficients are 1, 4, 6, 4, and 1. We should be seeing an interesting pattern. What would happen when now we go to a plus b to the exponent 5? Can you see enough of a pattern here from the previous examples to be able to write out what you think this could be? I want you to try it. Pause the video, take a couple minutes, try this, expand it out, and then play the video and see if you were right. Okay, let's see if you're right. Here's the expansion for a plus b to the exponent 5. Now we have 6 different terms, the coefficients being 1, 5, 10, 10, 5, and 1. I think you can see that these numbers are all coming from Pascal's triangle. Specifically, this is coming from row 5. It's the same as the exponent that's on the binomial. In the example where we had to the exponent 4, all those numbers came from row 4. But I want you to notice the other pattern. The different variables in each of the terms also share a pattern. Notice how the a term always starts with the exponent that's the same as the exponent that's on the binomial. And then for every term afterwards, the exponent goes down. The b term, on the other hand, doesn't even exist in the first term, but then every term after that, the number on the exponent for b goes up. This happens on every single expansion. So what do we have? We have the number of terms in the expansion is 1 more than what the exponent is on the binomial. Also, the coefficients that are found in front of each term can also be found in the row that is equivalent to the exponent on the binomial in Pascal's triangle. Finally, each variable has an exponent that either descends from high to low or ascends from 0 to the highest number, with the highest number being the same as the exponent that's on the binomial. Let's generalize this. Here's how we can generalize this. If we take any binomial a plus b to the exponent n, we can figure out what the expansion will be, knowing that, first of all, the coefficients in front of each term in the expansion relate to Pascal's triangle. So the first term will be n choose 0, the second term's coefficient will be n choose 1, the third terms will be n choose 2, and so on until we get to the last term, n choose n. The 2 variables in the expansion, a and b, will have a pattern as well. The first variable a will start with an exponent that is n, and then for every term we'll decrease the exponent by 1. So the second term will have a to the exponent n minus 1, the third term will have a to the exponent n minus 2, and so on all the way until it gets to the last term, where the exponent on a will be 0. Finally, b will work just the opposite of how a did, where it starts with an exponent 0, and every term thereafter will increase the exponent by 1 until it gets to the last term, where it's the exponent n. Another way that we can write this is using something that we call sigma notation, and it looks like this. Sigma notation is used as a quicker way of writing out a sum of different numbers that hold a pattern. This symbol here is recognized as capital sigma in Greek letters, but mathematicians know it as a symbol that represents the sum of. The letter that's written on the bottom of this symbol we refer to as an index number. Every time we want to add a different term, the index number goes up. So in our case, we're using the index number r, and it's going to start at the number 0. That's because our first term is n choose 0, so we want that to start at 0. And you can see that that choose always increases by 1. So the second term will be n choose 1, the next term will be n choose 2, and so on. So r will continue to increase by 1 every time we add a new term, all the way until it gets to n. So the top of the sigma notation tells us where we want to stop. We want to stop when r reaches n. To the right of the sigma notation is our formula. This is where we plug in the values of r and n for each term until we get to the end. So we're going to have n choose r, where r starts at 0 and moves all the way up to n, a to the exponent n minus r, and then b to the exponent r. When you go to university and you take math classes, you're going to be seeing a lot of sigma notation. So this is a good introduction to how it works. Okay, let's put all this stuff to good use. Let's see some examples. Example 1. Let's expand 2x plus 3 to the exponent 4 using the binomial theorem and combinations. In grade 11, you had done this before, where you drew out Pascal's triangle and then used that to figure out what the different coefficients were in front of each term. Now we want to try to use combinations instead. It'll be quicker, and we won't have to draw out Pascal's triangle, especially if the exponent is way higher than 4, if it's 8 or 12 or something even higher than that. Step 1. We're going to write out the expansion using variables a and b rather than the 2x and the 3 so that we can understand the pattern. Here's what that would look like. A plus b to the exponent 4 equals, and then we have 4 choose 0, a to the exponent 4, 4 choose 1, a to the exponent 3 times b, plus 4 choose 2, a squared b squared, plus 4 choose 3, a times b cubed, plus 4 choose 4, b to the exponent 4. This is just using the pattern that we know from the binomial theorem in the previous slide. You'll see that the first term and the last term only have one variable. The first term only has a to the exponent 4. Well, there really is a second variable of b, but it's to the exponent 0. And anything to the exponent 0 is just equal to 1. So really it will disappear. So we don't have to include it. But just know the pattern did exist. Okay, step 2. We now want to replace a and b with the actual terms that we were given in the question, 2x and positive 3. I say positive 3 carefully because if it was 2x minus 3, we'd have to replace b with a negative 3. So here's what that looks like when we take the same thing that we did in step 1, but we replace the a and the b with a 2x for a and a positive 3 for b. We have a lot of numbers going on here, so we have to be very careful when we expand this out, and that's going to be in step 3. When we do the expansion, just be very careful when we expand in the exponents. A lot of times we'll forget that the exponents around some of these brackets are applied to not only the variable, or the x, but also the coefficient. So let's see how this works. For the first term, 4 choose 0, well, anything choose 0 is always equal to 1, so that's equal to 1. 2x all to the exponent 4. Remember, this 2 is to the exponent 4, but the x is also to the exponent 4. A common mistake here is to write 2x to the exponent 4 as the expansion, but that's not true. The 4 goes to both the 2 and the x. So this turns into 16x to the exponent 4. 4 choose 1 is equal to 4. 2x cubed, remember it's 2x all cubed, so 2 cubed is 8, and x cubed is x cubed, and then multiply by 3. 4 choose 2 is 6. 2x all squared is 4x squared, and 3 squared is 9. 4 choose 3 is 4. 2x is 2x, and 3 cubed is 27. And 4 choose 4 is 1, and 3 to the exponent 4 is equal to 81. So our final step here is now to simplify. We can't leave it at this. We have to multiply all the coefficients together to get one number for each term. And there you have it. 1 times 16 is 16. 4 times 8 times 3 is 96, and the x cubed is there. 6 times 4 times 9 is 216. 4 times 2 times 27 is 216 as well. And 1 times 81 is 81. So that whole thing is equal to 2x plus 3 all to the exponent 4. And that's the proper expansion. Okay, let's take a look at one more example. Find the first three terms of the expansion of 3x minus 4y all to the exponent 6. This question is only asking us to figure out what the first three terms of the expansion are, so we won't need to do the entire thing. But one thing we're going to need to be very careful of is there's a negative sign in between both of these terms. So that means that the a term is 3x, but the b term is negative 4y. And when we plug that into our pattern, we have to remember to replace negative 4y into where b goes, not just positive 4y. So let's start with step 1. Step 1 was to write out the expansion of a plus b to the exponent 6. Because we only need to find the first three terms, I only expanded the first three terms. But I included this dot 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 at the end to just let us know that it does continue beyond that. Don't forget that if the question asks you for only the first few terms of an expansion. Next, step 2, we need to replace the a and the b with the actual terms in the binomial. So we're going to replace 3x into where a goes, and everywhere we see a b, we're going to replace it with a negative 4y. Notice how on the left-hand side, I've rewritten what the actual binomial is. I'm not saying that a plus b to the exponent 6 equals that second line, because that's just not true. Make sure that your notation, your communication is proper. Now we have to expand and simplify. So you're going to figure out what 6 choose 0, 6 choose 1, and 6 choose 2 are for the first three terms. Then you're going to take the exponents and expand them into the brackets. Again, be very careful and remember that the coefficients inside each bracket are also to the exponent that's on the outside. Here's what that looks like. Our last step is now to simplify. So we're going to take all of the numbers that we have in each of the terms and multiply them together. The second term is going to be the trickiest because it has that negative 4y as one of its coefficients. So if you see, we're going to multiply 6 times 243 times negative 4. And when we multiply all those together, we end up with a negative number. So the second term in this expansion will actually be negative. Here's the final answer. The final numbers are big, but because we went through all these steps, it wasn't that tricky. Alright, so now you've seen the connection between Pascal's triangle, combinations, and the binomial theorem. Good luck on your practice questions, and we'll see you next time.